Okay, so I guess let's get started. So welcome to another statistical seminar. It's my pleasure to introduce Dr. Kehui Chen from the Department of Statistics at the University of Pittsburgh. Her research interests focus on functional data analysis and network modeling. She recently works, her recent work includes variance and covariance analysis for multi-way functional data, repeatedly longitudinally observed functional data, and relevant hypothesis testing, model-based network estimation, and inference. Today, she's going to tell us about her recent work on interpoint-ranking sign covariance for test of independence. So let's welcome our speaker. So please take it away.
Thank you, Yang, for the introduction, and thank you for inviting me to the seminar, and thank you all for coming to the talk. So as Yang just introduced, my earlier work are mainly on functional data analysis and network data analysis, but today's talk is actually in a slightly or kind of different topic. It's not really about any of the functional data analysis or network data analysis in my earlier topics. So today I'm going to talk about interpoint-ranking sign covariance for test of independence. And this is a joint work with my PhD student, Hsic. Okay, great. So the outline of the talk today, I'm going to first review the sign covariance tau star introduced in this earlier paper. And this tau star, sign covariance tau star, has some very good properties we will see in a minute. It's a ranking-based test, and it's consistent for general alternatives, has a very nice interpretation. However, this original paper developed this sign covariance tau star only for univariate data. That means you have univariate X and another univariate Y, and the joint distribution is bivariate distribution. So in this talk, the main work here is to generalize the sign covariance tau star to multidimensional case. So it can even work for example, more general types of random objects, such as functional data. And at the end, I will give some numerical experiments and data analysis, and also we can see the performance of the proposed method, and also relative performance of some other methods, like well known in this field of test of independence. Okay, so test of independence. Here, we consider two random variables, X and Y, and with marginal distributions, Px on X and Py on Y. So we assume they have a joint distribution, Pxy. And in this paper, when we say test of independence, we are interested in testing whether this joint probability, Pxy, equals the product of the marginal distributions. So the null hypothesis is they are independent. Pxy equals Px times Py. And the alternative is that they does not equal, so they have dependence in some way. So we want to test this hypothesis based on an independently drawn sample from the joint distribution. So the notation here is x1 to xn pair, x1, y1 to xn, yn. And what we mean, we in this talk, we focus on like developing a consistent test of independence. What do we mean by consistent? So the dependence measure, or the population version here, we consider needs to be 0 if and only if X and Y are independent. So this is a zero equivalence property. And then the sample version, or basically the test statistic, will converge to the population version with certain rate. And then based on these two properties, we're going to have a consistent test against general types of alternatives. That means it can control the size at any fixed level alpha, and the power can go to 1 when X, Y are dependent. So more accurate mathematical formulation will be given later. Now let's back to the simple case, univariate case. So where we have a univariate X and a univariate Y, they both take value in R, the real line. Classical measures of association include Pearson correlation, Kendall's tau, and Spearman's rho. These are all very well known and widely used association measures between two univariate random variables. So however, these are not suitable for test of independence because these measures could be zero even if there are some type of association between X and Y. So they are generally not consistent tests like against general types of alternatives. So in the literature, two other alternatives, like when we want to focus on consistent test, two well-known alternatives, Hofstad's D measure and this BKR, what we call the coefficient. So these two are, most of the time they are consistent. For example, Hofstad's D, we know that they are it is consistent to, it has zero equivalence when you have the joint distribution to be continuous. But we also know that for some discrete distributions, Hofstad's D can also be zero even if there are associations. BKR generally is consistent for bivariate distribution. So, however, these two are they are not really widely used in practice because the formula is somewhat complicated. Especially the test statistic for Hofstad's D is basically a U statistic with order 5. And the BKR is a U statistic with order 6. And the formula is somewhat complicated without a very clear interpretation. So and both of them are ranking based. That's a very, in my perspective, it's a kind of a good property. Then today in this talk, we based on a newly developed ranking-based test, sign covariance tau star. So this is developed in a relatively recent paper, 2014. And since it has been developed, it has received quite some attention because this new coefficient, sign covariance tau star, is a modification of the Kendall's tau. And you will see in next slide that it has some nice interpretation. And also the corresponding test statistic is a rank-based U statistic of order 4. So that's a bit simpler than Hofstad's D and BKR. And also it is consistent against general alternatives when the joint distribution is continuous or discrete or a mixture of two. Actually, the author of the original paper also conjecture that this test is consistent for more general, even if it's not a mixture of continuous and discrete distributions for general types of joint distributions, although it's not actually proved in the paper. And so why we say it's like extension of Kendall's tau, because Kendall's tau is a measure that measure the probability of if you take two pairs of the data. So here, if we see this one dot here is one pair of the data XY and another pair of XY. If we take two pairs of the data, we compute the probability of these two pairs be concordant. So this is a picture of like they are concordant, and this is called disconcordant. If this pi d2 is the probability of two pairs to be disconcordant. So tau is the difference of these two. The Kendall's tau is the difference between the probability of concordance minus probability of disconcordance. And what about the tau star? This tau star consider 4 pairs instead of 2 pairs. So if you have 4 pairs of data, each dot here represent the 1 pair of the data, and then you have 4 pairs. So draw a line between if you look at X coordinate and draw a line between the smaller 2 and the larger 2, and also look at the Y concordance and then look at Y and also draw a line between the smaller 2 and the bigger 2. You have only 3 possibilities, these 3 possibilities. And we call these 2 as concordance pairs. So that's, this represent here is a probability of 4 pairs of data being concordant. So it's like the concordance pair, and this is called a disconcordant pair. So if you look at this, it's really like not clear relationship between X and Y. Okay, so this tau star has a formula that can be interpreted as the difference between the concordant pairs and disconcordant pairs with 4 pairs of data. Okay, so this is why tau star is like called a generalization of the tau. And it has an equivalent definition. Equivalent definition is tau star xy has this formula: expectation of a function of A and a function of B, a function of X and a function of Y. So there are 4 independent pairs xy from the joint distribution xy. This A function is defined as this. So this is exactly the same as the previous slide. The definition is equivalent. From this formula, we can see more clearly why this is also called a sign covariance, because this is a sign version of the well-known distance covariance when we consider only one-dimensional data. And in the paper, in the original sign covariance paper, it's proved that this tau star will be greater than 0 if and only if, and it takes 0 if and only if X, Y are independent. So this is a zero equivalence property, very nice property. Okay, so a bit more on the connection with distance covariance. So this distance covariance, since it has been developed, has received a lot of attention and many following up papers. The definition of distance covariance in the original paper is from the characteristic functions. So for X equals RP and X in RP and Y in RQ. And later, there are all other different equivalent formulation and equivalent formula. So this is one of them. So you can see from here that distance covariance can be defined as this. And this is just the Euclidean norm in P and Q, RP and RQ. From here, it's easy to see that distance covariance can also be written as 1/4 expectation of H function and another H function on Y. And this H function takes this form. These are the Euclidean distance. Now further, if we only consider P equals Q equals 1, because we were considering this univariate cases, P equals Q equals 1, this Euclidean distance here becomes just the absolute value. Then this H function turned out to be pretty much the same as the A function, except the sign. So earlier we can see that this tau covariance is taking this form, and the A is sign of this H function. So that's why this tau star is also called a sign covariance. This is a sign version of the distance covariance in some sense in the univariate case. Okay, so from here we can also see that distance covariance in univariate case is taking this absolute value. And when it goes to the multivariate case, we can change the absolute value to a Euclidean distance on RP or RQ. And we can even generalize to cases that other than the RP, RQ, even more metric in metric space. So this can be a general metric. This can be just a distance between Z1 and Z2 and Z3, Z4. So this way, distance covariance actually is defined for multivariate data, and also it's proved to be consistent against general alternatives with some condition. And here you can see one straightforward idea to extend this tau star to multivariate data would be also, we just generalize this A function. Instead of using the absolute value, we can use a general distance function here. Then that's sign. However, in the original paper, it's already been considered and actually showed that this tau star could be 0 if we just generalize this way. And it could be less than 0 if we just naively generalize this way. And the consistency property of the tau star test does not hold anymore. Then since then, it's a question, it's a topic of research. How do we generalize this tau star to multivariate data? There are some possibilities like explored by other paper. For example, these two papers, they are considering the the pairwise signal between the random variables. If you consider RP and RQ, then take one dimension from X, take another dimension from Y. So basically there are P times Q pairs. And if we only take one dimension, it becomes a univariate data. So you can apply this tau star on this univariate data. Then at the end, you can summarize, sum or take maximum or some other summation of the pairwise tau star. So this is mainly developed for mutual independence test, not exactly the independence test we are talking about here. And then for example, this paper, they follow the line of projection method. So you can project multivariate data onto a univariate, you can project multivariate data to become a univariate variable by projecting along some direction. And then after that, you can apply the tau star to this univariate dimension. And of course, there has to be a way to integral, to summarize over all the directions. And then some other methods, for example, these two, they try to build on this Holling's multivariate ranking. So basically, if you directly define ranking on multivariate data instead of univariate data, if you have the ranking, then this ranking is already one-dimensional, then you can directly apply tau star. So these are possible extensions, and the ones that I mentioned here are mainly developed for RP and RQ. So it's not suitable for kind of some other general random objects, for example, some non-Euclidean manifold data and functional data and so on. So here we propose a new interpoint-ranking some covariance that could be applied to more general types of random objects. And of course, it applies to RP, RQ as well. Some notations. So we assume that we have two separable Banach space, X and Y, with the norm and also distance notation, rho and zeta. And theta will be the joint probability measure. And we have marginal measure denoted by mu and v. So theta is the joint measure and mu and v is the marginal measure. So what is the interpoint-ranking some covariance? This is actually kind of also a straightforward extension. So we consider the original tau star formula, expectation between a function and another the same a function on X and a function on Y. But instead of directly applied to X1, X2, X3, X4, we apply to rho X0, X1, rho X0, X2, and rho X0, X3. So you can see here that we bring in another independent copy, X0, Y0. Original definition of tau star will use 4 independent copies from the distribution XY. Now we need 5 independent copies. X0, Y0 is an extra copy. So using this copy as an anchor point, and then we basically use the distance to induce a univariate random variable. If conditional on X0, fix X0 at this anchor point, then rho X0, X1, rho X0, X2, X3, X4, this are 4 independent copies and they are univariate random variables. So you can actually apply the original sun covariance formula. And this is just the regular absolute value. And what is the empirical version? When we have the, so the empirical version here we propose is HNXY. This is because the population version expectation. So it's pretty clear that this is the sample sort of average. This is a U statistic. We have a U statistic over order 5. This summation is taking over all ordered different integers from 1 to n. And this is the kernel function. This is the symmetric kernel defined on 5 independent 5 copies, x1, x2, x1, y1, x2, y2, and x5, y5. And this kernel, phi kernel is defined as this. So this is the summation over this A function product. This means product. So product of A function. And this A function is the same as before. Okay, an alternative formula. So for a fixed point xi, yi, we can refer to rho xi, x, and zeta yi, y as x and y interpoint distance arising from xi, yi. So this basically says when you have a fixed anchor point xi, yi, you can take the distance of all the other points with respect to this particular anchor point xi, yi. Then you got the what we call x and y interpoint distance. So these are one-dimensional random variables. If you define AI be the empirical tau star between these two univariate random variables, we have the empirical version of the tau star here, and we can see that our empirical IPR tau star is exactly just the average of all these AI, averaging over all the anchor points I. So from here, the interpretation of IPR tau star is pretty clear. This is a interpoint-ranking sign covariance collects the signal of dependency between x and y interpoint distances arising from all anchor points xy. So the proposed test actually only depends on the interpoint-ranking because original tau star only depend on ranking. And this R interpoint-ranking, Rij, is the ranking of the j's point, the j's xj, the ranking of xj with respect to, this Rijx is the ranking of xj ranked according to its distance to this anchor point I. So this is an interpoint ranking. Basically fix I, fix xi, take all the distance of all the other points to I and order them by the nearest to the farthest. So that's the interpoint ranking, and the statistic at the end only depend on these two interpoint ranking. Okay, so before I talk about the theorems like the large sample property and also their equivalence of the proposed test, I want to discuss a little bit of the general form. So here in this talk and also in our paper, we focus on generalizing tau star. However, this idea can be used to generalize other test statistics as well. For example, Hoeffding's D, BKR, and even the univariate distance covariance. If we consider X, Y are univariate, then these tests can all be written in a U statistics form, a U statistical form like of order M. So this is UM, and H is a kernel function. It's a kernel of order M. So how do we apply this idea? We can generalize to multivariate dimension or more general objects by introducing an extra independent pair. So then the U statistic of order M becomes a U statistic of order M plus 1. And this new pair here is YIM plus 1, YIM plus 1. So this kernel becomes a kernel with order M plus 1. The definition of this kernel is this. So taking over all the summation, all the permutation, it's a summation over H applied on the rho and zeta pairs. So earlier it's X1, Y1, and now it's rho Xj1, Xj2, zeta Yj1, Yj2 until rho Xj1, Xjn plus 1, and zeta Yj1, Yjn plus 1. So this is the new Xm, Ym. This is the new X1, Y1 in some sense. So this kernel H is as defined in the original UM. Whatever depends on like which one, which is the unit, what is the univariate measure? What is the dependence measure for the univariate data? This H is defined accordingly. And we can generalize to multivariate setting. So one particular thing I want to mention is that if we use this to generalize the univariate distance covariance, we know that the univariate distance covariance when R equals, when X is in R and Y in R, we can define the distance covariance accordingly, and it's a non-sign version of the tau star. So we can use this plus to generalize distance covariance to multivariate case. This is of course different from the original distance covariance in multivariate version. Distance covariance can directly be applied to multivariate data, and even if you use the same distance rho and zeta, these two are two different methods, two different tests. We only did a relatively small simulation, but according to our numerical results, this generalized one is this plus one is actually more powerful than the original distance covariance in multivariate setting. So also the original distance covariance require the space to be strong negative type to be consistent in general case. However, we don't require that anymore if you use plus one. I can only make this as a sort of a discussion remark here because I have to admit we didn't really fully explore this direction. We focused on the generalization of tau star because we want to focus on the ranking-based method. So here's the theorem, zero independent equivalence for this Interpoint-Ranking tau star. Basically, it says that if your joint measure is discrete or continuous or a mixture of the two, this pretty much is a condition we inherit from the original tau star. Then we have a probability mass function pxy and a density function. This is for the continuous part. This is for the discrete part. Our measure can be written as a mixture of the two. Then we have the zero equivalence. We say that RPR tau star xy is greater or equal to 0 with equality if and only if xy are independent. So here one remark is that we use this G abstract Wiener measure because this measure is a standard multivariate Gaussian measure in finite dimensional space. So basically, if we consider RP, RQ, it's just the standardized multivariate Gaussian. And this is equivalent to the continuous distribution definition in the traditional sense, in the conventional sense. So we use that here because this is extendable to separable Banach space even for infinite dimensional case. In the infinite dimensional case, for example, functional data, we don't have the Lebesgue measure. So we have to find some way to define this continuous distribution notion. And here, this abstract Wiener measure is an extension to the separable Banach space. And the good property here is that for any open set, it has a positive measure. So that's what we need to kind of mimic the Lebesgue measure to define this notion. And in the finite dimensional case, it's equivalent to the conventional definition. So the large sample theory for our test statistic, it's a very conventional notation that the kernel phi, we can define phi I. So basically for the kernel, we fix the first I pairs and take expectation over the rest. Then this gives us phi I. Sigma I is the variance of phi I. Based on the large sample theory of U statistics, if sigma 5 less than is bounded, then we have that this statistic Hn xy converge to the population version with a square root unconvergence rate. So we first look at the null hypothesis. Under the null hypothesis, the interpoint distances arising from any fixed pair x1, y1 are still ID and random variables. They are still independent. So the phi 1, x1, y1 basically is the tau star applied to the x1, y1 induced univariate random variables. So this phi 1, x1, y1 is 0. And this is 0 for any anchor points. That also leads to sigma 1 equals 0. So when sigma 1 equals 0, this is a degenerate distribution, and this whole thing is called a degenerate U statistic. That means our null distribution has to be from the degenerate U statistic theory. So our statistic is actually n times Hn xy, and if we can easily develop a test of independence based on this statistic, and it is consistent against general alternatives. Specifically, if x and y are independent, the null distribution is like this. It follows n times Hn follows a mixture chi distribution with the weights that are the solution of the eigenproblem. So this is pretty much from the U statistics theory. And if they are dependent, we have Hn xy goes to infinity. This guarantees the power when x and y are actually dependent. So a little bit more discussion on the power. We know that under the alternative, we have proved that IPR tau star is greater than 0 because we have the 0 equivalence. Only when they are independent, IPR tau star will be 0. So here it is greater than 0. However, how large is this signal? It's an important question. And we here mainly work with a constant level dependent signal. That means it's this value is greater than 0 equals C, some constant value. And with this greater than 0 based on this convergence rate, we can easily see that n times Hn goes to infinity. So we have power goes to 1. And we could also consider some local alternatives where the signal will be in the 1/n rate because we earlier have square root n convergence rate. So this is possible, but it needs some further characterization. And one thing I would like to mention that if x, y are in Rp and Rq with very, very big P and Q, even bigger than n, this IPR tau star can, of course, still, the definition still holds and the 0 equivalence theory still holds. We can still kind of compute the statistic because you can still define a rho and zeta for high dimensional data. However, the signal in these cases, the dependence signal may be very sparse, where, for example, the dependence only exists among a very small subsets of coordinates. Only like a very few coordinates will have a dependent with the other y coordinates. Then in this case, this signal, IPR tau star, although it's still greater than 0, but this may be very small. This may be actually in a scale of 1/p or 1/q or maybe 1/squared p or something. And then this power may depend on the ratio of P and N. So here we don't actually study this signal sparse, the sparse signal case. So this needs a further calculation of like the ratio between P and so on. So here if we still have a sort of a dense signal like IPR tau star xy greater than 0, some constant level, then we still have power goes to 1, and even it doesn't matter actually how large is P and Q. Okay, so the proposed test can be applied to more general structures such as functional data. And the functional data is intrinsically, we say functional data is infinite dimensional. And although this functional data is infinite dimension, it's very different from Rp, Rq, and PQ goes infinity because we have a structure for functional data. Like in earlier study of, like, for example, the covariance estimation for the large P, small n problem, sample covariance is not even consistent to the true covariance for large P, right? When P greater than n, you have to have some structure. And here, functional data, usually we have some smoothness structure and the sample covariance. Assume you observe the entire function, the sample covariance, sample mean of the sample covariance of just from the x1, x2, x3 from this function is actually consistent to the actual covariance kernel. So this is a point that functional data with this smooth structure, it's also, although it's infinite dimensional, it's different from this PQ goes infinity. And in functional data case, it does make sense to still consider this signal of dependence like is in a reasonable level. It's not in a very sparse case. So for example, if you have a function xt and another function yt, you want to consider the dependence between these two functions. It's not interesting to consider for a fixed t. You only have one point t that xt, yt are dependent, and all other points they are not dependent. This is not really something of interest in functional data settings. So usually you have at least a local batch that will be dependent. So that's why this is still under our consideration, and the very sparse signal case is not covered in. I won't say it's not covered, but it needs a further calculation of what is exactly the power, whether this still goes to infinity with a reasonable rate. Okay, so before I talk about simulation settings and some data analysis, do you have any questions for the method or theory here? So I assume there are no questions, and I will discuss some simulation settings. We compare this power and type 1 error with several existing tests of independence. Here I say compare. It's actually very hard to compare because it's just, you can have all different simulation settings. And here we mainly want to show that the proposed test is working and put in reference with some other tests. Not really trying to say that the proposed method is much powerful than other methods also. So here the distance, we compare with a few methods are listed here. The first one is a well-known method, distance covariance, DCOV, that's the original version developed in this paper. And later, of course, it can be applied to more general data other than RPRQ, as long as you can use the reasonable rho and the zeta. And then another one, the HSIC, the HSIC method based on our kernel. So here we choose Gaussian kernel, and this kernel is basically a monotone function of the rho. We use the same, all these methods need a distance measure between the data points. So we basically use the same rho for all these methods for comparison. But of course, the rho can be different for different simulation settings. And in this paper, they already show that HSIC and the distance covariance will be equivalent if you have a distance-induced kernel or kernel-induced distance. Here, certainly a Gaussian kernel here is not induced by this rho. It's not the kernel induced by this rho. So these two still have different performance, empirical performance. Okay, so another one we compare is the Hhg test. This is a test that turned out that it only depends on Interpoint-Ranking. So just as we did it in Interpoint-Ranking. And basically it divides, or using the interpair distance to divide all the data into a 2x2 square. A 2x2 square, and then use the Pearson chi-square statistic. So since you can divide in many, many different ways, then you at the end summarize all the Pearson chi-square statistics. So this Ball covariance test here, trying to, it can be viewed as a generalization of the Hofding-D method, Hofding-D measure in univariate case to multivariate case, or even beyond that. So it turned out that this test with the two recommended weights in their paper are also, this test only based on the Interpoint-Ranking as well. So these two are ranking based and these two are not. So these two methods and the one we propose in this paper, the Interpoint-Ranking tau covariance, sign covariance, tau star. So these are all based on Interpoint-Ranking developed from very different angles. So it's interesting. And then the simulation setting 1, we start with some traditional multivariate data. We have X and Y. Here we only consider dimension 5, and we also have results for like a dimension 20, 25, and so on. So sample size n is 20, 50, 100, 200. And we just use the regular Euclidean distance for X and Y with alpha equals 0.05 and type 1 and power based on 1,000 simulations. So here we quickly show, I will just quickly show the type 1 error. All these methods we consider here can control the type 1 error very well. So it's well below the fixed level alpha equals 0.05 for some different distribution and for different sample size. So this is the power figure. I don't know if it's visible here, all these lines. So we compare with the methods we kind of consider here are all supposed to be consistent, at least in RP-RQ case, proved in the paper. And we see that empirical power certainly have some difference here. We do see some difference. This is a linear case. So this data is from a joint normal with XY has some linear relationship. And we can see that's kind of the only case distance covariance, the blue curve here works the best. And then in all the other cases, distance covariance somehow is not working very well. And especially for some cases like the inverse of X case, the circle case, diamond shape, these distance covariance are not working at all. It's kind of, it has also been shown in other papers, but not clear the explanation or the theoretical reason why that's the case is not very clear. And then other methods, we can see that Hsic, the purple one, is a purple one. It works okay in most cases, and for some cases, the power is not increasing when we increase sample size. Of course, as I said, we only tried Gaussian kernel. Hsic is a family of methods, so you could try all different kernels, and maybe the empirical power will be different. And also, like the Born covariance method, here is green and yellow. It's kind of in the middle, the performance in the middle. However, again, this Born covariance method is a family of methods that you can have a weight in the integral. So it's a weighted integral, and this weights, you can choose all different weights. So here we only choose 2 different weights that's basically used in the original paper for simulation, and there may be other weights can consider. According to these simulation settings, we see here the proposed IPR tau star method and also the Hhg method are the 2 work the best. So these 2 are actually pretty close. The black line is the proposed method, and the red line is the Hhg method. The Hhg is the one that you cut into 2x2 table and use the chi-square Pearson chi-square independence test. So that these 2 perform pretty well in most of the cases and in the top group, and these 2 are actually pretty close, the performance. And in the linear case, they are not the best, and they are actually in the bottom. But when n increased to 200, the power also reached 200. Power also reached 1. Okay, so simulation two, we consider some manifold valued data. We consider variables on spherical coordinate of the unit spheres S square, and we use the great circle distance. So it's not Euclidean distance. And we also consider symmetric positive matrices, like then we use the affine invariant Riemann metric on this manifold. So these two, I list them here, but I'm not going to show the detailed results because the setting, the equations are pretty complicated, the setting of the relationship between X and Y. I will, due to the time limit, I will move on to the third simulation. It's a manifold valued functional data. So we have functional data xt. T takes value 0 to 1, but for each time point t, this xt is not on a Euclidean space, it's on sphere S square. So we consider this basically spherical functional data. And then you can see that the distance between two trajectories, there are different ways to define. We measure this distance by first point-wise using the great circle distance on the sphere, and then take sup over t. So this is the distance for the manifold valued functional data. So sample trajectories of spherical functional data like this, over time t, it's a curve, but on each time point, the data point lives on the S square. So that's a manifold valued functional data. And we want to test the dependence between X and Y. Y is just, here we only consider a scalar response Y. So different ways to generate this sort of dependence, and this first one is type 1. Type 1, it's well controlled. All the tests can pretty much control the type 1 error, and we're gonna see the power for these two settings. So the empirical power of the tests for IPR tau star, distance covariance, Hhg, bulk covariance 1, 2, and Hsic. So here, this case is like a relatively linear case, but it's integral over time t. And this is the results. We can see that the performance of all these methods are close. And this one is an inverse case. We have seen earlier that even without the integral over time point t, we have seen in simulation one that when y and x has some sort of inverse relationship, distance covariance is not working. And here we see that again. And the red curve is the Hhg, and the black curve is the proposed IPR tau star. These two are still on the top group and very close performance. So at the end, I will talk about a simple data example. So this data example is actually provided by Raymond. Raymond kindly shared the data with me. So the data set is described in his paper earlier. And in this data set, the annual yield of two major crops, corn and soybean, is recorded in bushel per acre from 105 counties of Kansas from 1999 and to 2011. So the weather data contains the daily minimum, maximum, and maximum temperature aggregated at the county level. So we have the temperature curves, x1t and x2t. This is, t is daily from within a year. So that's, we have 365 points, and x1, x2. This is the minimum, this is the maximum. Y is just the annual yield of the either for corn data or soybean data. Then we want to test whether this one has something to do with Y. Earlier, there are like work trying to model the relationship between Y and these X. And here we just want to test whether they are dependent or not. It's just kind of a simple data example. And we want to first define the distance between this functional data. First birate function xit and another birate function xi plum t. This distance here is not a Euclidean measure. It's It's not a Euclidean distance, it's a distance defined this way. So the key is that we take this temperature base. So temperature base is the crop specific base temperature, 8 degree for corn and 10 for soybean. And we take the positive part. So if it's below, it's 0. It's above, it's a positive value. The reason is that, so in these papers, they believe that if the temperature, average temperature drop below this temperature base, this corn or soybean, they do not grow. And if it's above, they grow. So that's the distance measured between two temperature functions. And we use the Euclidean distance for y. Then we just apply the 6 methods we mentioned in simulation to test the dependence. It turned out that all of the methods can detect the same statistical, detect the dependency between these two. And they all draw the same statistical conclusion at 0.05. So that's the end of the talk. Thank you for listening, and I'm willing to take any questions you may have.
Okay, thank you very much, Kehui, for interesting talk. And it's time for questions. So do we have any questions from the audience?
I have a question. Are these things difficult to compute for large data sets?
Oh, did I have one slide. Did I missed that here?
Well, I may have missed it.
I think I missed that. I didn't talk about that. Eh? It's not here. Sorry. So sorry, I somehow deleted that slide accidentally. So there is a discussion of the computational cost. Thank you very much for the great question. So we have basically our method needs to take like n times the time the original tau star takes. So we need to compute this tau star, the original sign covariance developed for univariate data, n times like when we take all the anchor points and anchor points. And the original tau star can be computed. In the original paper, it's actually pretty slow. And later there are other papers improve the algorithm. And for now, the best algorithm can compute tau star in n log n operations. So it's pretty much linear. It's very fast.
Oh, that's good.
And then basically, yeah. So basically, our method is like n times that. And it may be even because this is kind of a naive computation. We basically use the tau star package for n times. But if we closely study the formula, there may be faster ways to compute this IPI tau star, even faster than.
Of course, if n is really large, isn't it going to be hard to not reject independence?
Yeah, I think basically this exists in any hypothesis testing sort of framework, right? So when n goes really large, you can detect a very, very small signal in some sense.
Yes.
So yeah, I think that is probably true as well here. Yeah. So
okay.
Yeah.
Thank you.
Thank you.
Are there any other questions for the speaker?
Hello, I have a quick questions. So, so in the data, like there are like some other baseline variable, right? So, is there any idea to maybe extend the test to testing conditional independency?
Conditional independency.
Yeah. So like in the test, like so I guess like in lots of for example for the data sets, like there are some baseline variable like irrigations or not, type of thing?
Yeah, that's a very good question. And actually, conditional independence, there are some work, but conditional independence is impossible for really general alternative against all alternative, like without any assumptions. Like here we are basically considering a general type of alternative, any types of dependency, right? So conditional independence versus conditional non-independence, if you don't assume anything, it's impossible. And there are some work like working on conditional independence test, like some I know, like in using mutual information and so on. So I haven't tried to extend this piece of work to any conditional independence test setting. I don't know. I mean, I don't see an easy way, like to, for example, if you have a conditional independence test already in univariate setting, and then whether we can use this sort of interpoint idea to generalize to multivariate, I think my answer is I haven't really have a good answer solution to conditional independence in this setting. It's a much harder problem, I would say, especially in non-parametric setting. Yeah.
Thanks.
I have one more little question.
Sure.
If you're assuming that you have IID samples, and I mean, suppose you had a bivariate time series, which has autocorrelation. Does anybody do that sort of thing this way?
Sorry, what do you mean by this way? You mean so
well, I know, I mean, a lot of times you use spectral analysis and things like that, and I just wonder if there are rank-based things that people do.
For even in the univariate case, right? So like
yes.
even in
yes.
even in the univariate case, when you have autocorrelation sort of data, so it's I think I've read some papers, like they are mainly in econometrics, like literature and econ literature. They like you consider the correlation between two autocorrelated data sequence, and the Pearson correlation, for example, is not even like well understood, because it sometimes we call it a sparse correlation. It's actually, even if X and Y are independent, but because of their within autocorrelation, you actually see a positive Pearson correlation when computed just this way. And is there like a consistent test of independence when there's autocorrelation? I don't know. I don't.
Yeah, I mean,
I'm not aware of any kind of literature that could have a consistent test of independence in this setting.
Well, I don't. Yeah, I'm not sure I can answer that either. So thank you.
Thank you.
Well, just quickly follow up Raymond's questions for conditional independent test. If you have three variables, X, Y, Z, and you're interested in testing X and Y, whether they're independent or not, conditional on Z, I guess one, can you regress Z out from X and Y, then just test their residual for independence? I guess that's not fully non-parametric if you're using a parametric regression, but if you do a non-parametric regression and take the residual, then just test out using your procedure to test the residual, would that give a conditional independence test?
Yes, I think there are work on that regard. Like you need to take out the conditional, the effect of the set you want conditional on, right? So in the general like setting, when we consider general objectives or like multivariate setting, then without any parametric assumption, it's just difficult to take that effect out. And if you have some, you have to have some sort of assumption. and then it can, so it's the null hypothesis is of course conditionally independent, but the alternative hypothesis, there has to be some consideration. It's not general, or they are not conditionally independent. So that's a very difficult and specific, sometimes application specific question.
Mm-hmm. Mm-hmm. Thank you. Do you have any other questions for the speaker? Okay, if there's no further question, let's thank our speaker. Thank you very much. Very nice talk.